Good afternoon, everybody, and thank you for joining us. For those of you who don't know me, I'm Mark. Richard and I have been tag teaming, but we're actually supposed to be here today. So this was actually planned. Not the lecture, because I gave that yesterday, but this is a new one that I wrote last night. So I'm going to try it out on you for the first time. Just as a comment, if we go straight north from where we are right now, we will get to Winnipeg. So anybody who doesn't want to know where we are, it's straight directly south from Winnipeg. We're still in Mexico, which gives you an idea of how big the place is. 5 days and we're still in Mexico, even though we haven't actually been there. Richard commented this morning that he had been on a trip, and I can't remember where it was. It was somewhere west from Winnipeg, heading west to east. I don't remember where it was, but or east to west, should I say? And it reminded me a little bit of when I finished my graduate work. I did my undergraduate work at the University of Saskatchewan out in Saskatoon, which is about 8 hours west of Winnipeg, in a similar climate. It gets very cold in the winter, nice and warm in the summer, beautiful. Anyway, I took up a job as the first ever environmental person at a molybdenum mine in north central British Columbia. And back in the day, you didn't have the thing on your phone where you would plug it in. You had to go to MapQuest, right, to find out where you were going. So you went on to MapQuest to find out where you were going. So I went on to MapQuest and picked up my route. And I went on to Google Maps today to pick up my route, and I wanted to show you where I was going. I was going from here to Saskatoon, up to Fraser Lake, up in this particular place. And that was the trip. The interesting thing about the trip was the instructions. There's 3 of them. 1, 2, 3. The first one was I came out of my house, I turned right, and I went up to the traffic light. That was 350 meters. 350 meters, turn left. I then drove 1,422 kilometers, or 14 hours and 7 minutes. I then turned right and drove 500 meters. And that was it. I mean, literally. That was how I got from finishing up my university work all the way across Canada. And it really is sparse. There's not many people up there. And I had to have a stop. I ended up in a snowstorm right here in the Jasper National Park. It was the 28th of December, and so it wasn't very pleasant weather, but I had to stop right here in Jasper National Park before I continued on to Fraser Lake. And I had a very nice couple of years doing the environmental work at a molybdenum mine. The molybdenum mine had been open since 1963, and I joined the molybdenum mine in, what would it be, 1990, and I was the first ever environmental person to join the mine. So it's been open for all that time. So I had some fun developing the systems and developing the work. So that's really not where I wanted to do today. What I really wanted to talk about today is water, and the importance of water on a global scale and also on a local scale, more specifically related to the flow of water and the different systems that affect water and the animals and plants that live in that water as we move from the mountains down to the coast. Have a look at it a little bit. But one of the things that I found very interesting was when I looked at global water, I found this really interesting graphic. So on the left-hand side is all the water on the planet. Okay? So all the water on the planet is right here. It's a bar, all the way from 0 to 100%. 96.5% is in the oceans. To give you an idea of how big the oceans are, oh yeah, we've been sailing on them for the last 5 years, 5 days off Mexico. 2.5% of the fresh water, 2.5% is fresh water of all the water on the planet, just 2.5%. So then we'll come across to the next bar. So this is total water. This is fresh water. So then we look at the fresh water. And this is where the numbers get really interesting. About 70% is in glaciers and ice caps, 30% in groundwater, 1.2% of the freshwater, so 1.2% of 2.5%, do the math, it's not very much, is freshwater that's available to us. And of that, most of that is in groundwater and permafrost. So 70% is in groundwater and permafrost. So we're playing with this tiny little bit up on the top here. So you can see how important it is that this is the lifeblood for everything that's on the planet. Well, marine ecosystem accepted, of course. But for everything that's on land, if we ever get there, this is the bit that we're playing with, this tiny little percentage here. Most of it is in lakes and tiny little pieces in the atmosphere, swamps, marshes, and rivers. How does it get there and how does it get around? There's a thing called the water cycle. Go back to your grade, I don't know what, geography class. You've probably seen this, but I'm going to refresh your memories anyway. We've got water in the ocean and water on land. Doesn't matter what it is. It evaporates, it comes up into the atmosphere, and eventually it condenses somewhere in the clouds, and in this particular case to return to the ocean or to return to the land as precipitation. On land, you've got direct transpiration from all the plants. So plants give off water. As they do, they're taking it in through the roots, they're giving it off through the leaves. That contributes a little bit. You've got melting of the ice caps, melting of the snow in the spring. Some of it stays there, some of it comes off. You've got glaciers, runs off into the lakes. Some of it comes into the groundwater. Some of it comes back into the plants. Some of it comes back into the rivers. Few people know that groundwater is one of the major sources of water that comes into the rivers. The water comes up into the bases of the rivers. We know that because we've done a lot of modeling of it, and we can see the effects of groundwater when we build a mine. We can actually plan and program from the groundwater models. Some of the groundwater goes back into the ocean. So I want you to consider and keep it in mind that the whole system is kind of a closed loop on that little bit of fresh water that we have here. And remember, 8/9 of the planet is covered by the ocean, so most of the rainfall goes back into the ocean. So if we're going to look at river systems, we really need to understand a few basic terms. So the most important term is this term, a watershed. So a watershed basically outlines everything that is going into the main river system. You can define watersheds as small watersheds up in the upper part, or you can define the whole watershed from the source, which is the origin of the water, to the mouth, which is where it discharges back into the ocean. You've got a few little geographical terms. You've got tributaries, which is where smaller streams or rivers come together to form these larger rivers. And usually they do that at something called a confluence. And everything normally, we know that weather can change things, but normally things are confined to within the main channel. So concepts here, the watershed is the kind of the whole outline with the rivers, with its tributaries coming in, and we can order this as we go. There are two primary different types of water. There's lentic water, which is still or very slow moving. So think lakes, think marshes, think large bodies of water that move very slowly. So that's lentic. They're characterized by some layering. You can get layers in these lakes. You can get temperature layers. I don't know if you've ever been swimming in a lake and you've got that warm temperature layer on the top, and you stick your hand or your body down lower in the lake and you get that very cold lower piece. Well, you can get that both chemically. You can have something called a chemocline, which is where the chemistry changes, or you can have something called a thermocline, which is where the temperature changes. So chemistry will change at the chemocline, and temperature will change at the thermocline. There's usually a lot of oxygen at the top in lakes, less oxygen as you get deeper into the lakes. And nutrient cycling can vary within these systems. It depends on how much flow, what the inflow is, and that sort of thing. So you've usually got the edges of the lakes, which are very productive, down to where the light will penetrate, and then you've got the depths, the abyss in the bottom of the lakes, which are very low and productive. For these lotic systems are the ones that are flowing. The water flow influences the characteristics of what will grow in the area. So if you have fast flowing water tumbling over rocks, you tend to have higher oxygen concentrations because the oxygen is mixing in. If you've got slow water down at near to the coast, you'll have lower oxygen concentrations, and that affects the kind of life that you can get there. And oxygen is one of the key drivers to species in there. So you've got species in these lotic systems that are adapted to high oxygen, high water flow, and you've got other species that are adapted well to slow flowing, muddier, dirtier water. Think about the two different systems, but the systems all come together as a continuum. It's all a continuum. Usually there's not a clean break. Obviously when you come into when you come into a lake or a dam, there's a definite change in flow rates, right? And there's a definite change in water depths. But generally in a river system, it goes from this fast flowing narrow channel, and it gradually changes with slope, it gradually changes with energy as we move from the highlands down to the lowlands. And you can see here you've got species of fish like rainbow trout, which would be in the upper reaches generally, that's where they'll live, and they're adapted to faster flowing water. You've got some critters that will live up there, and we'll have a look at them later. So we can essentially split the river system into three different pieces, and we'll have a look at each one. You've got the steep slopes up at the source. Remember that from the first graph, from the first piece. Then you've got kind of what they call the mature stream in the center, which meanders a little bit, and it's got lower energy, lower flow rates. And then you've got the slow, what they call older type of stream, which is down towards the coast. And you'll see that as you go up to Antigua tomorrow. You'll see up in the highlands there, you'll see these fast flowing streams. As you get further down the mountains, you'll see the meandering like this. And finally you get down close to the coast where you'll see the marshes, you'll see the mangroves, and you'll see some of the other areas, right, that are there. At any stage you can get marshes, you can get all kinds of things. It depends on the geology, the underlying geology. So if we have a look at the faster flowing streams, you can see here lots of white. That means the air is mixing with it. If we look at the substrate is what's in the bottom. Big, chunky boulders, lots of energy, very little mud. If there's any mud, it gets trapped down in the bottom. And these are the high energy systems where you get, in what Richard and I are interested in, a few other people, this is where you get gold trapped in the bottom of these systems, because gold is heavy and it goes down into those slower flowing areas. But that's not what we're talking about today. We're talking about the system itself. Very, very high energy, lots of quick flow, and the species that live in there are specifically adapted to that. And these are an example of a few of the bugs that will live in the bottom of this. And you'll notice on some of these bugs slightly different adaptations. And you'll see here, this guy on the end has got like flat pieces on the legs. That one is a fast flowing water one, and the water flows over the top of him, and it pushes those kind of little wings there, push it down onto the rock. You get all kinds of different adaptations. These great big things here, the odonates, these are the dragonflies and damsels. These are bigger and bulkier. You tend to find those in the lakes, rivers, and marshes. And if you've ever walked by a lake and river, you'll see dragonflies, damselflies. These are the bigger critters. So looking at the form of the beetle, looking at the form of the insect, gives you an idea of where they live. A lot of these primary insects, they live on leaves that fall into the upper parts of the river. If you think about it, when we're up in that upper part of the river, there's very little opportunity for change in the organic matter that comes into the river. It's a leaf that's going to fall off a tree and it's going to, off it goes. It's not got a lot of chance to go through the different levels, the different trophic levels like we looked at the other day. So we're looking at these are the primary consumers. They'll eat the detritus that falls into the river. They'll scrape some of the algae that forms in the eddies around the rocks. But there's not very much that actually lives there in terms of total volume of animals or insects. And it doesn't matter whether you're in the highlands in a tropical area or in the highlands in a temperate area, you've still got that fast flow, high energy, high oxygen, and it's a fun place for critters to evolve to live in. So then we get down to the middle reaches of the river, and it looks like this. It's very pleasant. It's got a little windy piece. Reminds me of a story when I was at school. When I was at school, I had a geography teacher called Viv Hatton, and he drove a Lotus. I remember that because I really liked his car. He was a good geography teacher too. But Viv Hatton was a new geography teacher, and he only had one set of classes. Like he only had one set of lecture notes or teaching notes, which was grade 12. And I was in grade 6. So Viv had a very interesting philosophy. He taught grade 12, but he just taught it slowly. Right? So we went through all of this stuff on rivers. So I get to grade 10 and 11, and I'm taking geography, and I tell the teacher, well, I've already seen all this, she said, well, when did you see all this? I said, grade 6, and I got sent out of the class for being cheeky. Anyway, she subsequently made some inquiries and found out that Mr. Hatton was teaching grade 12 geography to grade 6 students, but he was just teaching it very slowly, and it worked very well. And this is why I have a love of geography right now. So if you look at these middle rivers, they're a little slower, they've got a little bit more structure, and they've got a lot more diversity in terms of the species that are there. You've got some plants that will actually live in there along the edges. You'll get some emergent vegetation. You'll get both terrestrial and aquatic insects living in there, which then give you the different layers. You may get some muddy areas where you're going to get mollusks, you may get crayfish, that sort of thing. But you've got different species living in there that are tolerant to slightly lower oxygen levels, and they're tolerant to, and they've got the opportunity to feed on a lot of different things. Up in the upper reaches, you've just got insects to feed on, maybe a little bit of algae, but down here, you're getting a little bit more diversity of feed. Often these sections of the river will go through a riffle and then a pool, and then a riffle and then a pool. So it's a very interesting piece because the riffles are really nice. They produce lots of insects in the riffles, and then when you get to the pools, it produces great habitat for fish. So when I'm trout fishing, I'm looking for the bottom of the riffles just before they go into the pool, and I'm looking for the eddies where the fish are going to be able to sit without losing too much energy. So going on to the next piece, which is it's my favorite piece of the river. It's the slower meandering pieces down on the coast. This is the depositional zone. It's depositing sediment, it's changing, it's meandering, it's moving all over the place. Lower energy, lower oxygen, and these, you can see here, there's a little deposit being formed there. There's another deposit being formed here. You can see all on the inside of these bends, these deposits happen. The water in these is probably a little bit cloudy. It's probably a little bit murky, but you're going to get some really big fish if you're a fisherman, or a fisher person, should I say. And you've got lower oxygen levels, especially in the summer, so it can be a bit tricky. One of my favorite features of this section of the river is the old Oxbow Lake. I don't know if you remember this back from school. You get these formations that you get areas here which are red, which are eroding, and then these areas of yellow, which are depositional. Usually you're in sediments that are unconsolidated because this is a depositional area, so the river has been through here already. And gradually what happens with time is this bend cuts out, and it cuts, and it eventually cuts off and then flows straight through. It then finds another meander to develop and go, and you end up with this beautiful thing called an oxbow lake. Why it's called oxbow, I'm not really sure, but I think it's something related to the harness that we put on an ox, and it becomes a geographical feature. This is somewhere in England, and they've actually, you can see the old road that used to go around the river. The oxbow lake is here, and the old farming patterns remain in the center. And this obviously now has become waterfront, and because it's in England, it'll probably last for a long time, because there's lots of rain. Looking at the animals and plants that live in these downstream areas, you've got a lot slower flow. You can get a lot more diverse species here. Pike, you've got lots of, maybe you get mollusks, you get worms that live in the mud on the bottom which form food, and you'll get both emergent vegetation and like this Elodea canadensis, Canadian pondweed here, that will be on the edges of the rivers. And this gives you a very diverse array of habitats. You've got lots of different niches for all of the organisms to live in, and you get this beautiful, slow-flowing area, and you can get some very, very big fish in those areas. It's lovely. I was fishing in the lower reaches of one of the rivers in Venezuela, where I used to live, and I hooked something, and I thought I got the bottom, and it wasn't. It was a catfish, and it took me about an hour to get this catfish back up off the bottom. And in the lower reaches of the Fraser River, just outside of Vancouver, there's a very famous sturgeon fishery where you can go and catch sturgeon, and sturgeon feed in the silt and the mud on the bottom of the river. And I actually caught something that was about 2.5 meters long. It was quite a bit. It was a very, very big fish. It was like pulling in a log. It wasn't particularly nice, but I got a good photograph at the end, so that was what it was all worth it. And that's all catch and release. Same as the fishery off Guatemala, the sturgeon fishery in Vancouver, just outside of Vancouver, is all catch and release. So one of the most important features that we get in these freshwater systems are the freshwater wetlands. And when I say a wetland, there's a whole variety of them. I won't go into the tidal marshes, and I won't go into the freshwater marshes, but we'll look today I will look at the freshwater marshes, and I won't look at the tidal marshes because we're looking at freshwater today. So wetlands are generally dominated by grass-type species, lots of emergent vegetation, fairly shallow, with lots of areas of open water in between. It's really crucial for biodiversity, and I've mentioned a couple of times about these ecosystem services. And these ecosystem services is a way to try and get us to understand the services that these ecosystems provide. In this particular case, they're slowing down, so they're providing habitat for fish, for young fish. They're providing a lot of insect areas for growth on the emergent vegetation, and we're also getting cleaning up of the river systems. So marshes are very, very important in cleaning systems. They will clean pollutants out, and there's lots and lots of different types of freshwater systems, and I just put a few of them up here: marsh, meadows, prairies, and even things down to prairie potholes. One of these interesting ones is these fens, what they call fens and seeps. These are characterized by alkaline waters. They're very low in nutrients, and they have a very, very diverse array of vegetation that lives there. And if we look at what lives in wetlands, it's way more diverse than almost anywhere else on the planet. We've got all kinds of things birds living on fish, living on toads, frogs, that sort of thing. And we're really getting this diversity of species. And as we talked about previously, the wetlands that we're talking about in various areas form these things called Ramsar sites. They're designated as Ramsar sites. And they're high biodiversity pieces, and for migrating birds, they're extremely important. There can be adverse effects to draining wetlands, and we do have a habit of draining wetlands because we want dry land, or we want areas for agriculture. We want to be able to graze cattle on wetlands. If we have wetlands, then we tend to lose the cattle. If we drain them, then we tend to be able to keep the cattle because they don't walk very well on water. But you have a different effect. These wetlands act as big sponges. So we get a lot of rain. The wetlands act as a sink. So it's like filling up the bath. You fill up the bath, it's no problem because eventually it all goes out through the tub, through the drain plug. If you don't have the bath to fill up, it's all over the floor. And what happens when these wetlands are unable to accept the rainfall that's coming, you get the flooding in the downstream areas. So high rainfall events, historically, they would go in and fill up the wetlands. They would be into the marsh areas. There would be vast areas of wetland. We've taken those out, so now we have vast areas of wetland in our towns. I wanted to talk particularly, and this is going back to one of my favorite species again, about the effects of key species on a slough, and this is an elkhorn slough. This is Monterey Bay up in California. This particular slough is located right here. It looks a little bit like this, and it's tidal, a little bit tidal, so we're in that kind of marginal piece. But we've had a remarkable change in this since we brought sea otters back. So sea otters have come back into Monterey Bay area, and they've come back up into the Elkhorn Slough, and they've started to eat the predator invertebrates that are on the bottom. And what we've seen is that erosion in these areas has slowed dramatically because the plants on the edge are not being eaten, and they're able to establish solid root systems. And it really is stabilizing this whole marsh area back to where it was. Before, the sediment was all going back down into the ocean, and it's the opposite of what we were expecting. If you have no sea otters, you get erosion, you get high nutrient levels going into the ocean, and you get poor quality marshlands. With the sea otters, they come in, they've allowed the vegetation by being predators. You can see them both eating here. They eat the invertebrates, and what they've done is they've made it more resilient. The nice thing about it is, as it becomes more resilient, it is able to also accept more flooding. It acts as a resource for us because it's providing ecosystem resources as a flood prevention area. So we bring these key species back in, and it helps the overall ecosystem. And I did want to have a look at one key engineer in the aquatic system. In this particular case is Castor canadensis, the North American beaver. And this is a keystone species in engineering of systems. It's the ultimate, I think, builder that we have apart from ourselves. But this one is not a particularly destructive one unless you happen to have a cattle area that's getting flooded by the beaver dam. But we can control those things. This is one of the few species that actually modifies the environment to suit itself. It likes ponds, it likes water, and therefore it modifies the environment. You can see a big flat tail here to help with propulsion. It's got nice big feet. And if you look at the pointy end, it's got a big set of teeth that it has to keep chewing, or it would die because the teeth keep growing. So if we look at the way the beavers work, they have the dam here, and they raise the water level around. They're cutting trees adjacent to, but they're essentially creating a marshland area in areas where they weren't before. They live in something called the lodge. Here's a photograph of the lodge down in the bottom. And the lodge has underwater access only. So if you can't swim, you can't get in. So it's really cool. The beavers come up and they live in this nice dry area. There's a little ventilation area up in the top, but essentially they're safe from predators. There's not very many swimming predators. And people have started to look at these, and they've started to look at the beaver dams and the benefit that it goes upstream because we're developing marshes, and they've actually started to develop their own beaver dams. And you can see here, either the beaver was very, very advanced and had cutting tools, right? Or this is crazy, right? This is absolutely crazy. This is a man-made beaver dam. They're putting beaver dams in areas that they need to have modified where we can't get beavers right now. So they put this in, and what does it do? It's got huge benefits. It allows better infiltration of water into the water table. So if you've got a water table that's been damaged, you put beaver dams in, or you bring you bring a beaver in and get them to do it, because they're much cheaper labor than getting a whole crew of people to come in that need overtime and need bathroom facilities. But then you can also have areas back in here, they're a little cooler, and you get increased biodiversity. There can be problems with fish migration, but you can mitigate that as you go. And there's even a little thing here about how to live with a beaver, all right? You know, protect your trees, don't eliminate the problem. So you know they're going to cut down the tree, but if you put some wire around the tree, they won't be able to get to it, so you can protect your trees. You can control the water level, and this is not computer generated, by the way. This came off an actual piece of information that I got. So what we're trying to do is we're trying to do things properly so we can coexist with nature. But what we're really doing here by protecting beavers is protecting wetlands. And I did mention the introduction of beavers, and this is a different species of beaver. Castor canadiensis is the Canadian one. Castor fiber is the European beaver. Then they've actually reintroduced species up into Scotland, and there's been other releases of beaver. I don't know what you actually do. You go over to France, you catch a beaver, you bring it over, and then you release it into the river system. But these areas have been released, and they're releasing beavers actually into the systems right now. It was the 1300s that beavers were actually hunted out in Great Britain, and it wasn't and they managed to last in Scotland until about the 1600s. But now they're reintroducing them into Scotland. There's a plan to reintroduce them into England, but people are a little bit wary of it, a little bit like wolves being reintroduced into the Colorado ecosystem again. Climax predator. People are concerned about wolves. They're concerned about how it's going to affect their livestock, their lives, and really the impacts are minimal. And in this particular case, with proper management, you can control beaver affecting farmlands. You can control beavers affecting your roads and rivers. And they're actually releasing these beavers. It's a big thing. You can see lots of people with lots of cameras and all that kind of stuff. So it's a really popular thing. And research into the place in Scotland where they've released it show higher biodiversity. They show better use of areas by waterfowl and, interestingly, by bats. And there are impacts on some fish as well, getting better fish production. But there's also a little bit of a concern about the beaver dams blocking off fish access. So, it's in England now. They're doing this thing called rewilding. So they're taking an old golf course and they're planting the golf course to old trees. It's a very interesting thing because Britain has gone from not wanting to have any kind of wildlands except for in areas a long way away to rewilding, and this is one of the key species. This is a keystone species that's being brought back into the rewilding in Britain. I want to have quickly a little bit of a look at pollution in water, what we're doing with water. You've got here the general water system that we looked at before, and this is primarily looking at nitrogen. We've got lots and lots of sources for nitrogen, and I'll show you why nitrogen is important in a minute. But you're getting runoff from towns, you're getting runoff from agriculture, fertilizers, and that sort of thing. And then in these intensive fish farms, you're getting a lot of fish crap in the water, to put it bluntly, right? Which is a high source of nitrogen because we're putting a lot of fish food in there, which can affect the local system. Now, we're not looking at that particularly today. What I want to do is I want to have a look at this as on the next slide, which is eutrophication. You've probably heard about this. It's a word that I learned probably 20, 25 years ago when I was studying ecology. But essentially what we're doing is we're increasing nutrients in the water. When we increase nutrients in the water, it's great for plants. It's absolutely fantastic for plants. Plants love it. Nitrogen, you put a little bit of nitrogen on your lawn turns this bright green. You put a little water on, it grows, and you have to pay the next person to cut it, and then you keep doing that as a cycle. But what happens here is these algal blooms, you get algal blooms on the surface, and you get phytoplankton, which are little critters. The problem with these is they don't have, because it's a bloom, because it's something that's unusual, it doesn't have the predators, it doesn't have anything to eat it. And so it drops down to the bottom and starts to decay. It uses up oxygen, and it decreases the oxygen in the lakes. So that's why eutrophication is a bad thing. It increases the productivity of the vegetation, but it also decreases the oxygen. What needs oxygen to live? Basically all fish, all invertebrates, they all need oxygen in order to live. So you can kill off lakes by eutrophication. So we've got to be very careful. There are also some interesting changes, and I won't go into this in too much detail because I'm running out of time, on climate change in the area. You have earlier snowmelts which come through the rivers more quickly. You have changing rainfall patterns, particularly like in the northeast. And even on Vancouver Island, I've noticed that the climate is changing from its normal, what it used to be a little bit wet in the summer, wetter in the winter. It's now becoming more Mediterranean, where we're getting longer, dry summers, and then very, very wet winters. So we're getting all the rainfall that we used to get, but we're getting it in a more concentrated time. The other thing that we look at is what we do to systems to make them more efficient. And I love the more efficiency in biological and ecological systems, because in terms of biology and ecology, this is a great system. It's got lots of diversity, it's got lots of production, but we don't like it because, I'm not really sure, maybe it's navigation, maybe it's community, and what we do to it is we do that. We straighten it out. We straighten it out, we put dirt on the side of it, and then if it dries out in the side when we put this canal through so we get a lot of water coming through, it allows us places for livestock, it allows us for places to build, but unfortunately when there's a lot of rain, the water comes over the banks and we get these increased flooding events. So not only are we getting climate change affecting flooding, but it's what we do to the systems, right, that changes that. We're losing the capability, we're losing that buffering capability when it rains a lot. And that's why we're getting a lot more systems. I just wanted to have a quick look at dams. There's a move in many parts of the country right now, in many parts of the US and Canada, to remove nuisance dams. There are some very, very important dams for hydroelectric. There's very, very important dams for flood control. But there are a lot of dams that were built in the 20s, 30s, and 40s that are just dams that were built with no real reason. And a lot of them have filled up with sediment before. These big dams, they change groundwater. This is the system above. You can see the groundwater here. When you build a dam, you get a groundwater mound coming, but unfortunately in the downstream area where you've got a straight channel, you get a decrease in groundwater. So if you were drawing groundwater from down here, before they built the dam, you may not be able to draw it later. And there's a move afoot to start to remove dams. I always love the sight of machineries working in river, but that's an environmental concern, obviously. But this is the dam. This is the Klamath Dam in California, and they're actually removing an old dam that was put in. It really wasn't for anything except probably originally for watering of croplands above. If we remove the dams, we get better access to aquatic ecological resources, and then we've got this ecological resource that can be then fish passing and all that kind of stuff can really help. When we build our towns, we love pavement. We love pavement, and this is, I just want to have a think about how we affect this. If you look at this particular development here, there's parking for vehicles. The problem with parking for vehicles is, where does all the water go? When we have a big storm, all the water runs off the roofs, it runs off of all of the parking areas, it runs off the roofs here, it runs off the parking areas, and it goes quickly into the rivers. Again, when it goes quickly into the rivers, it's an instant response to a rainfall. It's not, if we didn't have, on my front lawn, when it rains, the water doesn't run off. It kind of slowly infiltrates into the groundwater, and then it acts like a sponge. But when we put this kind of thing, and then we are very surprised that at some point we get floods. Actually, in Denver, they charge you for putting hard surface on your private property. If you put hard surfaces on your private property, like sidewalks and that sort of thing, or if you pave a driveway, yeah, you get to pay more taxes, because then they have to deal with the water. If you've got soft surfaces, or surfaces that will infiltrate, you don't pay any taxes on that. So almost all of my property is soft surfaces. I'll tell you that, because I don't like paying taxes. So let's have a quick think about where we've gone today. We've gone through the 3 stages of the rivers, if you remember right back to the beginning, for those of you who are still awake. We've got that very fast, high energy piece at the top with substrate, lots of insects, aquatic animals that are adapted to high energy, high flow rates, rainbow trout. Love fishing up there. It's beautiful. It's a fantastic place to fish. We then come down to these middle reaches, what I call the middle age of the river. Get a little slower. We don't do as much damage, but we've got a much more diverse habitat, and this is where you start to get your wetlands coming in. And then finally, right at the bottom, we've got the old age river with its oxbow lakes, its beautiful oxbow lakes, its marshes. It cleans everything up, it deposits stuff before it flows into the water. Just remember that these beaver dams are part of nature, they're part of the system, and we have to really remember the power of nature and the power of water. We've seen a lot of floods, we've seen a lot of very damaging floods in the last couple of years, I think, and it's all because we're not listening or watching what's going on in these river systems. You build a camp right next to a big river that's got flood banks. That camp's not going to last very long. If you really listen to what's going on and look at what's going on, you'll see that the power of nature can be to benefit of us, and if we look after it, can be the benefit of future generations. So thank you for that. Thank you for joining me today. I hope I've been a little bit of help.